Okay, good afternoon. Last time we talked about how some of the physics models that we studied in this course were incorporated into a tool called the compact model for MOSFET, or SPICE model. And that model is used to simulate circuits. And I sort of explained its importance as serving as a bridge between the technology world in the semiconductor industry and the design world. Another purpose for doing that or going over this model really is a review of some of the things we have done, and also opportunity to introduce some new things. Now, today we're going to continue with that, and the first thing is a new thing. It's called a gate dielectric tunneling current model. You know, as a result of transistor scaling, the gate oxide has become thinner and thinner. And I think you have seen several reasons why we like the gate oxide to be as thin as possible. Is that right? Okay. So for that reason, we're using very thin oxide today, maybe 20 angstrom in thickness. And when oxide is so thin, turns out the currents can flow through the oxide, and it's no longer a negligible phenomena. And it's no longer just a physics issue now. It's even becoming a circuit design issue. So as a result, BSIM-4 actually has the gate dielectric tunneling current model in this circuit simulation model. Right? It's actually there. And the behavior is the following. If you look at lower right corner, or maybe start with the physics, turns out as a result of the research students identified, there are several paths for tunneling. Now, we're looking at the energy band diagram, as you already recognized, I believe. On the right-hand side of diagram is the substrate, yeah? The usual band bending, you see that, right? In the middle, we're showing the energy diagram of a thin dielectric, let's say silicon dioxide. On the left-hand side, it's heavily doped, M+ doped gate material. All right? Yeah? And this happens to be biased in the I suppose, the inversion regime, right? Okay. Well, it turns out the most obvious component of tunneling is the top component. That is, you know, there's inversion layer, a lot of electrons at the surface, and these electrons can tunnel through this barrier, get into the electrode, the gate electrode, and that becomes a current flowing between the gate and the substrate, for example. Excuse me, I'm sorry. I pointed in wrong direction. This is the gate, of course. Electron flowing from the inversion layer to the gate, or gate flowing from the, or the current flows from the gate into the inversion layer. Is that right? Okay. And indeed, this is a very large component because this current flow has the smallest potential barrier. The other two components have larger potential barrier, but has been found to be also very important depending on the situation. For example, if this was a PMOS rather than NMOS, then this component cannot be dominant, right? Example. Well, it turns out there are two other components important. One is for electron to flow from the valence band of the substrate and tunnel into the conduction band of the gate, okay? And the other is for electron to tunnel from the valence band of the gate into the valence band of the substrate. This last component may be called hole tunneling. The first component may be called electron tunneling because it's an electron on one side becomes electron located on the other side, or a hole on one side becomes a hole on the other side. The second mechanism is really unusual. It's electron, or maybe we can talk about, you know, once it's motion of holes as far as substrate is concerned. But certainly on the gate side, we're only talking about electrons. Right? But those are three important components. So the model in SPICE actually includes three equations for the three components. they have almost identical form, the three equation or three terms, but they have different barrier height, and actually they have different tunneling electron effective mass. It turns out the electron effective mass depends on its location relative to the valence band and conduction band in the oxide. When for the first component, you can probably guess that the tunnel electron mass is maybe similar to the conduction electron mass in the oxide. For the bottom mechanism, perhaps the effective mass for the tunneling electron tunneling hole is close to the effective mass of the hole in the oxide, right? And in between would be between. So the effective mass is also different. And when these equations are put into the model, this is kind of a behavior. We see the solid lines are the model, and the dots are experimental data. You see here we're looking at a range of our oxide thicknesses. Now notice how rapidly this tunneling current is increasing as we reduce the oxide thickness. You see how rapidly we're doing this? You know, between a 37 angstrom and 25 angstrom, that's almost just about one generation of technology, just about. And notice how many orders of magnitude tunneling current has increased. See that? Now you can see why this is a serious concern for the future, going into the future, all right? Extremely strong function of the oxide thickness. And this model, we're able to model many other details of this characteristics because considered all three components, and PMOS and NMOS both work very well. Now this is the interesting thing. You know, the data were taken by the students here. But when we look at this, we had a hard time understanding whether this is real or just some well, you may call it bad oxide or something that's not intrinsic to the oxide tunneling. And we kind of put our faith in the understanding of the physics, saying that if we don't see why it should be there, there must be just something bad with the samples that we have fabricated in the quarry hall here. And indeed, later when other users compare the data with their samples, which are probably made better in industrial laboratories, there's not that little blip here. So this is the example where your model can be more accurate than data if you can think in those terms. On the right-hand side is some additional data here. This is provided to us by Texas Instrument, and they compare this model in solid line again against data they get. They plot this in an unusual way. Well, not a usual way. They plotted it in a linear manner rather than a log manner. And actually, comparing data against model in the linear manner is often more stringent a test, because in the log plot, you can often fudge things. But in a linear plot, you can see the change of signs, current actually change signs, depending on VG and depending on VD. You can believe that. Near the source side, maybe the current is flowing from the gate into the source. From the drain side, current is flowing from the substrate or from the drain into the gate. So depending on the voltage, the gate current can either be positive or negative. And so model and the data agree quite well. So this is the gate tunneling. Now, let me mention something interesting about modeling. Let's say, so far we have talked about gate current as if we're dealing with a capacitor so far, although the Intel data did not look at capacitors, truly a transistor. At least the way we discuss it as if it's about capacitor. In a transistor, two things are different. One, you would say the channel potential is different. Is that right? As a result, then you say we just sum up, integrate the current at each elemental channel region and get a total current. There's nothing wrong with that. That's fine. But more interesting question is the following. Suppose there's some current flowing between the gate and the channel. Doesn't matter what's flowing into the channel, out of channel, doesn't matter, right? Suppose we have current. Should that current be taken out of the source or taken out of the drain current or evenly divided between those two? Just what is it? In other words, suppose we have, let's see, what's a good way of putting this? Let me think. What's the best way of describing this? Okay, I think this is fine. All right, let's put it this way then. Maybe I should even say, what about, when we have a gate current flowing into the channel, is that going to influence the source drain current? Beyond the fact that there's additional current due to the gate, what about the initial current? Would that be disturbed? After all, the initial current is a very peculiar solution that happens to satisfy all the requirement of Q inversion and the field and the mobility and the velocity to get a constant current. Remember that? Now we have this additional third thing coming in from the side. Is it going to modify that? So this is actually not an easy question, and actually considerable work has to be done to model the effect of the gate current on the transistor IV. Next topic is GITO. GITO is a model that we have talked about, and you can see it fits the experimental data quite well. Again, this is data provided by Texas Instruments, testing the BSM4 model, fits quite well. But there's one thing that the model we talk about so far does not cover, and that had to be included. In the model for GITO, you probably remember, we had a model that says this leakage current, or this GIDL current, let's say. GIDL current is, let me just say, it's proportional to exponential, let's see, how do I do this? Let me try this way. Let's say minus beta divided by the vertical field. And a vertical field, we say, is VDG divided by 3 times of T ops, or something like that. Right? So according to this model, it can be this current will be a function of VD, will be a function of VG. And turns out it's very accurate. And so this is good enough for SPI simulation. But what's missing, you notice, is that there's no body voltage, right? In other words, even if the body and the drain are at the same voltage, according to this, there will be same current flowing between the, by the way, when I say body, because the current is flowing between the drain and the body, right? So it's kind of a drain-to-body leakage. But according to this, even if there was no voltage between the body and drain, there's still going to be this current flowing between them. Now, physically, that's not possible, but when one thinks about it, turns out it's not possible, because if we don't have voltage between gate and drain, then the junction, the MOS, will not be in deep depletion. The reason it's in deep depletion is because of the body bias. If not in deep depletion, there will not be a band-to-band tunneling. So we do know, actually, data certainly says that if we plot this GIDL current against V, let's say dB, all right, or VB, let's say, or VDB somehow, fix the VGD, fix the VGD, the change in VDB. What turns out is true, and when VDB is large, it's independent of VDB, okay, which is why in the model that we presented to you in the textbook and in the notes, we didn't include the body bias, because it's not considered a big problem. But when VDB is small, eventually this will drop to 0. As a textbook model, this is sufficient. As a circuit design model, it's not, because circuit designer wants to use the model at whatever combination you can think of. Once the model has to fit, right? You just cannot say this is not, that larger region, and there's no particularly interesting physics there, therefore we can ignore that. You cannot. You still have to be able to model this right. So a graduate student did additional work here and put in there. So this model actually also is a function of VDB. Okay, you may want to think about, if you want to model the VDB in GITO, what's the physics involved here? What's going to make the current go to 0 eventually, and how you might want to model that body bias dependence, right? Now the next bulk of today's discussion, I think I'm going to spend quite a bit of time on this RF model. RF is, of course, a very important application for IC in recent years, and will continue to be important because of the wireless, the radio applications. It's interesting that for decades, people have been using SPICE to simulate MOS circuits and using the SPICE model. No one ever expected that an analytical model can describe MOS performance to a gigahertz. So the expectation is always it's good for DC, it may be good for some digital applications or baseband analog applications. When you want to design RF circuit, you better switch the simulator to something maybe based on table lookup S parameter or something like that, right? In the SPICE model, a set of equations, how can you do that? But of course, that's not very desirable because for many reasons, if you want to use table lookup, you lose a lot of the continuity in the characteristics, and doing optimization of the circuit design is difficult. Table also has the disadvantage in that you will not be able to filter out bad data as easily as you can do with a physical analytical model. In other words, it's true that especially in cases like RF where measurement is very difficult, you can imagine if you don't have a model, it's going to be very difficult to just have very clean data, and you don't know whether the data is really that accurate or not. So there's a lot of reasons to want to make the SPICE model work for RF circuit design. And when we look at this, what's needed to make the SPICE model to work for RF, well, it turns out there are two things that's needed, and I'll explain to them what these two things are. They're quite a bit complicated. Well, first of all, let's just look at the IV characteristics, all right, the AC performance as far as that's concerned, and later I'll talk about noise. As far as the AC behavior of the transistor concerned, turns out what you need is you want to include resistance in the gate, but I'm going to explain what this resistance is in a moment. And then also you want to model the substrate resistance better. These are the two things. And for low frequency operation, you don't have to worry about that too much. For example, for DC operation, you just say there's no current going through the gate, that's it. For lower frequency AC operation, just model the gate as a capacitance, that's good enough. Well, it turns out for high frequency operation, it's very important to include the gate resistance. Now, what's interesting about this is that it's easy for people to see that there's resistance in the gate because gate electrode has resistance. It doesn't matter whether you use polysilicon as the gate or silicided polysilicon as a gate, there's always going to be some resistance in gate electrode, right? So it's very easy to see you should include that. It's not so easy to see that this actually is not the main resistance in the gate impedance. This sometimes, in our experience, only 10% of the gate impedance. Gate really impedance is something else. It's intrinsic. Even you had a perfect conductor as the gate, a metal, something more conductor than metal, you will still have a large resistance in the gate in the behavior, and that's called intrinsic input resistance. And I'll explain what this is in the next slide. All right. So you start with the very accurate basic low frequency model. Then you have to model the input characteristics, and after I describe that, you will see why that's important to RF behavior. Well, turns out what's happening is, well, maybe I will do this way first. First, let me just say, let's assume all we have is the gate resistance. All right. Let's understand why the gate resistance is important for RF operation. Well, it turns out it's very simple. The reason is at RF frequency, there's significant amount of current flowing through the gate, right? Just because gate capacitance, there's current. Because of this gate current, there's going to be voltage drop across the resistance in the gate. As a result, you don't see the full voltage across the dielectric, so you don't get as large a GM, and your performance is degraded. Is that right? Simple as that. Okay? All right. So turns out the gate resistance, the way perhaps you're thinking about gate resistance, is not important, because it turns out it's a small part of what's causing the voltage drop. Why is that? The reason is this. As that gate current flows through the gate resistance, right? This may be due to the polysilicon resistance. As said, that's not a dominant component, certainly not an interesting component. There's still going to be voltage drop as a result of this AC current flow. What is that? Well, where does this AC current flow? It will flow from the source, voltage source of the gate voltage across any of these this polysilicon resistance, or even if there isn't any of there, that's not N. This current will flow across the resistor, a capacitor, and then reach the ground. But between this point and the ground, there's still resistance, isn't there? Isn't there? So as a result of that, the voltage drop across the oxide, let's say at this point, is not the full VG, but VG minus the voltage drop due to this resistor and the AC gate current. You follow what I'm saying? In other words, this resistor has the same effect as the polysilicon resistor, right? But in terms of a compact model, of course, much easier to put that resistor on the gate side, not put it into source or drain side, because otherwise you're going to mess up the DC characteristics. Is that right? So you're going to put this on the gate side. So although this is a gate resistance, but it's not due to the gate electrode. It's very important to recognize that. So we coined this name called intrinsic input resistance. There's a longer name called channel reflected gate resistance. And that's fine. Whichever speaks to you will be okay. We use both, all right? So intrinsic input resistance, which is a reflected channel resistance. But that's what we're saying. So we want to model that, all right? Then the question is, how do you model it? That's the question, okay? Well, of course, trying to make the long story short, because we're talking about really just a resistor. There's nothing to do with frequency, it's just a resistor, the way I described to you. So you would expect this resistance, this intrinsic input resistance, really just to be the channel resistance, except it's a distributed resistance, in the sense not all the gate AC current flows from the drain all the way across to the source. Some start from the drain side, some start from middle of the channel, some flows across the gate capacitor near the source. So this resistance is going to be less than the channel resistance, a fraction eta. Is that right? Expect that, okay? All right. And finally, there's a question about what is channel resistance are we talking about? Are we talking about RDS, which is the small signal resistance, right? DVDS. Is that what we're talking about? Or should be just ID versus VDS? Right? Okay? And some, or what? And so when you think about that, turns out because we're just talking about resistance. Just if you understand the reason we need this resistance, just to say when the current flows through this, it's going to have some IR drop. So if you think about that, then the resistance we're talking about truly is just this. Or VD over ID, I'm sorry, not ID over VD. It's really just VDS over IDS. And this is really nice because SPICE already models IDS very well within 2%. So we can model this very nicely. All right? So no additional modeling to do. And the next question is, what about in the trial in the saturation region? Should we still use VDS over ID sat? Or should be VD sat over ID sat, or should be VDS over VD sat over IDS. Right? Something to think about. Maybe you want to think about, and if you have questions to ask, can bring back for discussion. Okay. So this is what we decided to do. It really should be VD sat over IDS in here, and this is again very nice. This really makes the whole model just totally continuous because IDS is a continuous function in SPICE already. So we take advantage of that, and don't try to express this in terms of Cox, L, and W, and mobility. You do that, you necessarily introduce a lot of approximations. Don't do that. Just take advantage of what we already have in SPICE. Right? So the mobility doesn't come in. We just directly take the ID. Next question is, what is the factor? We all expect this to be less than channel. What is it? Well, can do some simple analysis to try to estimate what it is. But if you do that, you have to assume probably constant mobility, or that sort of thing, in order to simplify the math. And you can come up with number about 12, or you can use 2D simulation to get a better number. You may get up something like 14. So 14 is used as default value, right? Of course, just like any spice parameter, if you think you have better data, you can extract a number that you have more faith in. By all means, do that. You think 13 is better, then do use 13. But we think this default is very good. So even if you don't have any data, by the way, we think that if you just use this model, you're already going to get a kind of result I'm going to show you later in terms of comparison, right? So this is what we see using the default model with, in this case, let's say we're comparing against, I think this is actually experimental data. So here we're looking at the measured input resistance, and by the way, input impedance, or the real part of the input impedance, and this is measured by the usual network analyzer, starting from S parameter, convert to Y parameter, then you can get the real input resistance. If you measure that, it turns out it's a function of VG, and it's a function of channel length, and agrees with the model very well. So the fact is with VG clearly tells you it cannot be just the gate resistance, it cannot be the gate electrode resistance, right? I use the word electrode to emphasize just due to the poly resistance, let's say. Cannot be that, right? That would be a function of this. Whereas this channel resistance is a function of VG and VD and channel length and channel width. Another interesting thing is the dependence on L. Let's think about this L dependence a little bit, shall we? Okay. All these devices has the same W. So I'm going to draw you a top view of the transistor. Top view of the transistor is this, okay? This is the gate electrode finger. In the middle is made of polysilicon. Source on one side, drain on the other. You following me? All right? Now, we all know what the gate electrode resistance means. It means from wherever you're measuring it, flowing along the length side of the gate electrode. Is that right? Right? Knowing this is the cost of the gate electrode resistance, do you think this resistance will become larger or smaller as L gets smaller? I'll let you decide which is the L dimension in this plot. You should get familiar in thinking about it. What's the L dimension in this plot? That's right. This is the L. Is that right? This is the W. Okay? Familiar with this layout, looking at that, right? So as L gets smaller, W is the fixed. Does the gate resistance get larger or smaller? Yes, electrode resistance gets larger. Is that right? Right? Narrower fingers will give you a larger resistance. Now look at this experimental data. What do you see? The largest resistance is triangle. It's the longest channel. The shortest channel is the square. It's lowest resistance. You see what I'm talking about? See what I'm talking about? So clearly we're not talking about gate electrode resistance. Okay? So this is where a lot of people went wrong when they were trying to model this. If you truly treat this as a curve fitting model, of course, doesn't matter. Just pick one particular resistor to happen to fit that particular S parameter data that you have with particular channel length, particular VG, particular VD is fine. But that's actually the wrong physics. Physics is telling us the resistance we see in the input is the channel resistance. Therefore, the channel resistance, now think about the real resistance now, it's the channel resistance, remember? What the gate really sees is the channel resistance, right? Divided by eta. Now the channel resistance does become smaller or larger when L gets shorter? Smaller. And that's the only reason why shorter channel lengths give us better RF performance. That's the only reason. All right? Okay. That's why we want to go to a smaller one. That's the only reason, I'm sorry, because the intrinsic FT already is function of the channel length. We want a smaller channel length. But this actually how will I put it this way? Let me put it this way. All right. In other words, I won't do that. Okay. As a result of the gate impedance, the transistor lose more performance in the long channel transistor due to that effect than short channel transistor. Okay, going to short transistor make this gate impedance effect less important. Okay, so that's that. All right, and from this analysis, one would gather that this input impedance should not be a function of frequency, and indeed, when you look at this, it's not a function frequency, right? But if you don't have a model, well, you're going to have to think a little bit about, does this really mean this is not a function frequency, or should I construct a table lookup model to actually capture this data? It would be very difficult to make those decisions, right? Because we know the physics, then we know it's just a resistor. That's what we're talking about. Very easy to model after, very easy to explain, shall we say, but actually took a whole year, right, before we can reach this conclusion. It's really this simple. It's all that's needed to be done, okay? Yes?
I thought that some data actually has a lot of frequency dependence in this R.
See, this is the interesting thing. The question is, do you believe physics, or do you believe the measurement data? So the question is, how many measurement data have you looked at, and do they all show the same trend? And that's why I say table lookup sometimes is considered the most accurate model. It's really not, and that's a very important concept. Okay. Table lookup is not necessarily more accurate than something that's based on analytical equation. All right. So intrinsic input resistance is strong function of bias and decreases with decreasing L. If you don't think about it, there's nothing interesting about it, but it turns out it's opposite trend, right, with the gate resistance. Gate electrode resistance contribute only about 5 to 8 ohm in this case, and the total resistance could be 50 ohm in this one particular example, right? And there's one single analytical equation models RI as function VGS, VDS, and L. And the single equation, by the way, is really just this, no ifs and buts. Okay, it's that simple. But really made this become a contender for RF design model now. So if you look at the more detailed analysis, we see the real part of Y11 or inverse of that actually is the input resistance. But you can see that as function of frequency works very well. And for each case, we give two devices, 2.7 micron and 0.64 micron. This is for the so-called scalability test, right? This one model, if it's right, you should agree with any channel length. Is that right? Okay. So, and if the model is right, then it should fit frequency. Now, frequency part is especially interesting. We actually expected that this model is only good for a certain frequency range. After all, by choosing this model, we have limited ourselves to a single pole kind of model, only one L, right? One R, one C. Is that right? Right? And we know that there's going to be limitations because the behavior of the transistor is such that we know in a very high frequency regime, it's going to performance to degrade faster than that. What we don't know is that how good it is up to what frequency. A better question to answer or ask is, to what fraction of VT is this model good? Not to how many gigahertz, but rather to what fraction of VT. If it's good enough to 50% of VT, then we think it's going to continue to be good up to 50% VT as we scale our technology as VT increases. But it will continue to be good to 50% because it's not the absolute value of gigahertz that's important, but it is how close we have to match the physics of the transistor. So up to what fraction of the FT this model is going to break down. And this is where this long channel transistor is actually giving us some particularly interesting data. For the short channel transistor, for the long channel transistor, the reason is that the data we have is limited. We have data, I guess, in this case, up to about 5 or 6 gigahertz, right? That's measurement limit, so 6 gigahertz. But turns out the FT of the long channel transistor has only FT of 6 gigahertz. So we actually had the data all the way up to the FT of this one transistor. And we can see it's good almost all the way to FT. And that's not a trivial thing to say. I actually expected, I told the students, I'll set a goal to match this data up to 30% FT. Okay, that's what we want the model to work as the minimum. But looks like we can use this model almost all the way to FT, and that's very, very nice. Yes.
What's FT?
FT is called the cutoff frequency. That's the frequency at which the gain falls to 1. And so it's kind of a measure of the performance, speed performance of a transistor. Typically, for quarter micron transistor, let's say you actually can see it right here, FT is perhaps 15 gigahertz, and the FT increases roughly linearly with the gate, or inversely scales with the gate length, right? And but FT doesn't mean this is the kind of circuit. Circuit can work all the way to FT, because at the FT the transistor base is no good. So transistor circuit usually is designed up to a fraction of FT, perhaps only 10% of FT. All right. So it's important to bring the FT very high in order to design transistors to operate at high frequency. Okay. All right. So you can see this simple addition to the transistor immediately made the transistor accurate from all the way to close to FT. But you have to be able to model the transistor value correctly, right? Model its VGS dependence, L dependence, right? Yes. Yes.
Why this model doesn't have anything to do with Y22 and Y26? Is there something else that we're missing in the RF model that would have fit Y22?
Yes, the next slide we'll get to that. All right, good, very good. So this is actually compared with the entire model. We don't have any. This compared with the BSM4 model. So the other part of the addition that have to be added is the substrate network. All right, because R22 had to do with the output characteristics. And what is turns out what's important is that we cannot say between the source or drain is what people usually think about. We think source is also important, because there certainly could be circuit configurations where the source side is not grounded. And we cannot model this simply as a diode. Specifically, as a result of the capacitance, there will be current flowing from the drain into the substrate. And we cannot assume the substrate is just a perfect ground. We have to model the resistance. And after looking at this resistance, we decided really, ideally, there will be a network of 5 resistors. It's not obvious that one need all 5. In fact, there are some papers that says, even 1 resistor significantly improve the accuracy of the RF modeling. Others would say probably use 3. That's probably a good compromise. Some actually think it has to be 4. So BSM just allowed all these to be fitting parameters. That's really what it is. And in fact, allow you to use either 1 or 2 or 3 or 4 or 5 of these resistors. And this is one area that BSM cannot give the user a default value. Well, we can give a default value, but we cannot give the scaling behavior, because we haven't figured out how to analytically model the 3-dimensional picture of the current flow here. To some extent, it's the simplest of physics. It's just modeling the current flow in a 3-dimensional structure. You want to find the resistance. There's no question about diffusion or drift or impionization. Simplest physics. But we actually found that's mathematically the most challenging problem. We don't know how to come up with the equation that we have confidence about giving us a value. If I just tell you the doping concentration, give you the R and W, give us a value. Right? So this is definitely an area for research. Okay? Substrate modeling. Right. Okay, any question about this? All right. So this is one circuit level verification. It's Jing Ao, Paul Gray student, did this study with Xiaodong Jing, who developed this model. And this is a no noise amplifier, and using a 0.6 micron technology, a TSMC technology. And this is the voltage gain versus frequency. This is the measured characteristics. Both these are simulation. This solid curve is simulation with this gate input resistance and with the substrate resistance network, and this dotted curve is without those additions. So that's the kind of difference it makes. All right. Okay. Any questions? So, this RF modeling using compact model, when the problem was, I guess, offered to us by the user perhaps 3-4 years ago, looked like a very, very difficult problem. It's something that has not been able to, no one has been able to do for 20 years. And indeed, in working out the model, I think we learned a lot of new things. But the result is a very simple model. Other than we don't know how to predict these values, resistor values. The physics certainly is there, but we don't know how to put them in a analytical manner. But as far as anything else, everything is happening in the channel, in the gate, turns out surprisingly simple. Okay, so what has to be added to make the transistor model work all the way to 10 gigahertz is surprisingly simple. Okay. All right, if no question, let me move on to another topic related to RF. Well, it turns out for RF circuit design, accurate noise model is very important. To some extent, noise eventually becomes limiter of all circuit design. All right, if you can have zero noise, then you need very little power to transmit, and you can have a very large distance between the base station and the user, and everything is just wonderful. Right? But in reality, we have noise, so noise therefore has to be really modeled accurately. Noise is a topic usually not taught in a textbook and in classes, as maybe partly as a result of that. There's not much research in that. The model people use actually still trace back to 20 years ago. Van der Zeel did a lot of pioneering work, and people use that model. But users have always been complaining that it's not accurate, especially when channel is short. People use this term called excess noise. Just means anything that's understood. It's called excess noise, right? So as part of this RF modeling, the same student also looked into this noise model, and again, we learned even more about the noise model part. So now we have a model that we think is very physical, that fits the data very well, don't have to adding any excess noise, and we call this holistic noise, thermal noise model, and you will see why we think it's holistic, what it's considered, and again, the result is in many ways surprisingly simple. The concept is the following: is you start by dividing the channel into small segments. Each segment is just an independent noise source. Each segment is a resistor. Any resistor has produced a thermal noise. And according to the Nyquist theorem, very fundamental theorem, a elemental resistor will give you delta VD or delta VD square, which is equal to 4 KTB is the bandwidth times the resistance, the delta R. Delta R is the incremental resistance of that segment in the channel. All right, it's very elemental concept. It's okay, right? A related concept, basic concept, noise is that if you look at the thermal noise in current, then that's equal to 4 KTB over delta R. These two expressions are equivalent. Right? You should choose whichever model that's appropriate to use. If we're dividing the channel into many noise signals in series, which do you think is more appropriate? Do we want to model them as a series of current sources in series or voltage sources in series? Putting current sources in series doesn't make sense, right? How can you put a current source in series? So clearly we shouldn't do that, right? So the first thing you would agree is that you're going to put them as independent voltage sources in series. Is that right? Okay? As long as these are independent noise sources, then it's very easy to show that the current noise voltages should be simply sum of these incremental noise. In other words, the noise power is additive, not noise voltage is additive. All right? So you just add the noise power together, and you end up with this. Very simple. Again, it becomes very simple. No ifs and buts. I tell you, in the literature, there's been lots of debate about in the noise whether one should use DC current impedance or AC impedance. Some people even think should be GM. Other people should use the linear region of ID versus VD in this just the slope. And I think those of you that have studied RF or thermal noise know what I'm talking about, right? Anything you mention, someone is using that as a model, just because they're all based on. They said, oh, I think this matches with this experimental data better, or that paper said matches data better. Problem is that it's unfortunate the data first was not very accurate, and authors tends to just put the best foot forward, saying every paper say this model matches the data. So it becomes really difficult to say what is right. Okay, but if you think about the physics, as far as the voltage noise is concerned, there should be no question you should do this. Unfortunately, voltage noise is what designer wants. Designer wants to have a current, noise current in this transistor. So you say, gee, how do we do that? This is where the problem comes in, you see. So some people say, I take the voltage noise divided by the channel impedance to give us the noise current. Now in that case, this question, should I divide it by the AC impedance or not? So maybe we should say it should be this divided by the small signal resistance to give us the channel current noise. I've never seen anyone use that. That would be an interesting argument. But in reality, if you look into this, this is how you relate the noise voltage to noise current. Okay? Turns out you want to think this way. There are several reasons this noise voltage is going to produce noise current in the channel. There are several reasons. One reason is simply because, gee, if I have a transistor, and now we have a noise voltage in series, yeah? This is our noise voltage, suppose. Then, of course, I should have a noise current, which is simply equal to the noise voltage, perhaps divided by the channel resistance. In that case, I will use the small signal channel resistance. Does that make sense? You know, if this is my IV curve, if there is this noise in the VDS, then of course current will have a noise. Is that right? But is that the only thing? That's not the only thing. Why did I put the noise source on the drain side? What if I put it on the source side? If I put it on the source side, shouldn't there be another reason why there should be a noise current? Why? Because this VGS will be amplified by the GM. Do you agree? Right? Since the noise is distributed, some of them should be on the source side, some should be on the drain side. You see that? That's one reason. Okay? Turns out it's also very important, if you want to model this right, to remember that anytime you have a noise on the source side, not only the front gate can amplify the signal, the back gate can amplify the signal too. Okay? That's why in this course I emphasize the back gate. It's very important to do that. If you don't do that again, you will not match your data. You're going to say the model is not right, there's something else, there's excess noise. All right, turns out back gate is also amplifier. The same reason the front gate will amplify this noise, give you a current. Back gate is also giving you this. So there's something called back gate transconductance. In other words, if you apply a gate voltage to the body, you will find the current to change. That gives you another transconductance that we call GMB. You all know what GM means. You put an AC voltage on the gate, you find AC current in the drain. That gives you a GM. If you put AC voltage to the body, you also find the AC current in the drain. That will give you the backgate GM. So both of these GM amplify this gate. Question, yes?
Why would we assume that GMB has the same or even nearly the same frequency response as GM?
By definition, both GM and GMB are measured as a result. If I put a voltage source here, suppose I put a voltage source here. I used this figure before. Let me do that. Put a voltage before. By definition, it is going to be amplified by the front gate through GM and amplified by back gate through GMB. I did not say GM and GMB are typically very similar in value. GMB certainly is expected to be smaller in value than GM because the front gate is thinner than the back gate. All right? But in terms of the form, it should be identical.
No, not in terms of form, in terms of frequency response. Why would we assume that GMB would have a multi-gigahertz response?
There's no reason for it to have any less, any more frequency response. As far as noise is concerned, that's a good question. Maybe I should think about it more carefully. Maybe we'll have to think about it more carefully. We haven't. You will find out the model that we presented here has no quote-unquote frequency response issue. All right, that's a good question. Maybe we can discuss this a little bit in the discussion hour. I will not be able to give you answers. I'm really just listening to what you have to say. So right now, let me just tell you what I prepared to say. All right, in this discussion, there's no frequency discussion other than what Nyquist said, that this is a white noise, that for any given beta, then there is. Okay, and what I think Turi just mentioned, again, is another reason why in the literature there's a lot of discussion how to model this thing. There's a lot of uncertainties, right? But you will see why how we confirmed, verify this model. So we can see that this noise voltage is translated into the current in three ways. One is amplified by the front gate. Two is amplified by the back gate. Three, just as a result of the RDS or GDS. Remember what we said earlier? Yes. Anytime there's output GDS, then a AC variation in the VDS is going to give us an IDS. Is that right? Yes. So what does beta mean? Now this is coming to the compact model. Now in order a compact model, we have to be able to model this in a simple way. So we know, doesn't matter what fraction of this noise source we put on the source side or drain side, both of them will be translated into current through GDS. But only the fraction put on the source side will get amplified by GM and GMB. Is that right? Is that right? See what I mean? The part that's on the drain side will not be amplified by GM or GMB. Is that right? Right? So beta is just a fraction that should be amplified. In other words, depending on the channel, some of that you expect to be more close to the source, some of that you be more close to the drain. Is that right? So the challenge remaining is to figure out expression for beta. Right? Very similar to the eta we got in the previous equation. You can always do something to try to figure out what fraction is effectively amplified through the GM, what is not. Right? That fraction is called the beta right now. Is that okay? Right? So conceptually, we just divide the noise voltage into two parts. One part we'll put in the source. Okay? One part, effectively, we can say we'll put in the drain. We don't even put in the drain. You will see later for other reasons. Whatever is needed, we just translate that into the additional gate current. This term, we just put into the additional into the noise current. By the way, this is a standard way designers like to use. They need a model to model the transistor noise in this manner. Okay? Up until BSM4, no one has done it this way, so this is absolutely new to BSM4, all right? We think this is the right way to do that, right? So this automatically take care of the good GM, accurate GM the BSM already has. Don't try to express that in terms of mobility and all that. Then you lose all the advantage of all the good physics in BSM, right? So put it in here, and BSM will take care of GM, right? The common model cell will take care of GM, okay? All right, so that's the basic concept. And if you do that, Well, I'm telling you, there's another thing that's very interesting to think about in terms of the noise. For a long time, people realized there's something called a gate-induced current noise. That's very important. So far, I have just told you these are the three ways for the channel noise to produce noise current. Turns out there's a fourth mechanism. This fourth mechanism is this way. If we have noise voltage in the channel, through this gate capacitor, when they induce a noise current in the gate circuit, wouldn't they? If you put noise sources here, voltage source, wouldn't they produce a noise current in the gate? Of course they would. Now, if there was no resistance in the gate, then there's no problem. This gate current simply flow into the ground, does nothing. But if there's any impedance in the gate circuit, this current is going to generate a voltage at the gate. Is that right? IR drop, so-called. Yes? Now we have a gate noise voltage. Can you see that? And that gate noise voltage is going to produce a gate noise, a drain noise current through GM. Can you see that? Right? Okay. So this is a very complex thing to model. This is called the gate-induced induced gate current noise. So let me first ask you one question. If you can answer that question, I think you really got this very, very totally. Earlier we have said there are two components of resistance in the gate. Do you think both of those two, one is the gate electrode resistance, one is the channel resistance, do you think both resistance should be used to multiply this induced gate current in order to calculate the gate voltage noise? Or just one of them? If so, which one? I'll make it easier. Let's start concentrating on the gate electrode resistance, just the polygate resistance. Is that effective in translating this gate current into a gate voltage? You know, because the noise source forces the current flows through the gate circuit, because poly resistance, would that then produce a voltage? Yes, right? Absolutely right. Harder question is, will the channel reflected resistance does that? And it's a little harder to think about it and give the answer. Turns out, to think enough about it is not. All right, it's not easy, and certainly this is a result of many research meetings before we can reach that conclusion. It should not be there. All right, the effect of the channel resistance. Again, once you really think about what I told you about why we need to multiply by resistance, is the current multiplied resistance in the circuit gives you the voltage. If you think in that terms, then it has to be only the poly resistance. Of course, the signal source has impedance will also be included. Is that right? Okay. So the channel reflect resistance should not be in it. Yes, question.
So you're not modeling this as a voltage. This is in the simulator. It's a shunt current, and you're saying
exactly. So now the question is how we're going to model that. So the easy way to model that is to really just rely on this to model it. We already have a voltage, noise voltage here, and we already have a capacitance as standard part of the VSEM model, right? So this automatically will create a current in the gate circuit, right? Do you see what I'm saying, right? And if we can make this capacitance link to, if we have two components of capacitance, this is electrocapacitance. This is the channel reflected capacitance, right? Where do you want to connect the capacitor to? In the past, we always just connect capacitance between the source and the gate. Doesn't matter where in the gate. But now we have several possibilities. We can connect over here, point A. We can connect the capacitance to point B. We can connect to point C. Where should we connect it? B, right? So that this current only flows through the gate electrode resistance. See that? So this is what has to be decided. Is that right? And if you do that, and then turns out in order to do that, there's a compromise. What we needed for beta to model this right is not the factor we needed theta to model the induced current right. So we have to compromise which one we want to use. Turns out the two didn't differ very much, all right? And so I have to compromise which one to use. Another interesting question, I want to just introduce this question to you. Anytime you talk about multiple current sources, there's the issue of coherence. Now, are they independent or dependent? If they're independent, they're called incoherent. All you do is you add their current power. You add the noise power. If they're coherent, if they are not independent, then the noise actually is much larger, right? The same thing as this is a surprising thing to sometimes to people, but it's a fact. Let's say you have two signal source, let's say antenna, let's say, all right? One will produce a electric field of 1 unit, another produces an electric field of a unit of 1, right? If they are coherent, they're going to add together, and the electric field becomes unit of 2. Power will be 4, because power is proportional to the electric field to the power, second power, right? So these two antennae, they're coherent to give you a power of 4. If they're incoherent, just two separate antennae, each give you a power of 1. You only get a power of 2. You see that? Same thing with the noise. So it's very important to be able to figure out whether they're coherent, not coherent, and they're coherent. How do you model their coherence? Yes, question.
But if they're coherent, they're opposite signs, then you have 0 power.
Exactly. So you also have to figure out what they are. So it's very difficult. Most people can agree that the gate-induced noise is coherent with the channel because they came from the exact source, right? But again, if you want to make the problem complicated, then you can start to not knowing the sign and all that. But if you just follow what I said, really the current is both come from the same source. One is amplified through the beta only, the other is through this capacitor, then multiplied by the resistor, then through the beta. And in fact, our model didn't even say through that. We even allow you to have any complex impedance in the whole current path. So the signal phase can be whatever it is, right? So automatically we want SPICE engine to take care of that coherence. You see that? Right? And this automatically the coherence is taken care of by the SPICE engine. If you put a two separate current source, as people tried to do in the past, now you're going to have to figure out how to the coherence. And in fact, SPICE doesn't never add things in a coherent manner. SPICE engine can only add the current. They don't add power, right? They don't add the noise power. They only add noise current. So these are the, I'm sorry, they only add the noise power. They cannot add noise current. But by doing it this way, automatically coherence taken care of, right? Including the effect of the impedance of gate circuit is included. So this is how Beeson modeled the thermal noise. We call this holistic because this one model actually, combine the channel noise and the gate noise together, and also it automatically includes all the details that's included in the DC model, because everything is based on just DC current, DC voltage. You see that? Both this noise, right? So anything we have done in the DC case, whether it's short channel effect or whether it's a velocity saturation, hot electron effect, automatically have been added to this. So for this reason, we call this a holistic thermal noise model. All right. Now, I'm making it sound easy. As I said, it's a PhD thesis here. We just describe this in 10 minutes. Sounds like everyone should be able to work out from top to bottom just in 3 slides. That's not the case. Of course, a lot of work is doing on that. And part of that work is experimental verification. You want to make sure that you see enough data and that you are confident with what your assumptions are. So here is some of the experiment data that Xiaodong Jing collected. And I will not go into the detail what this means. The minimum noise and optimum impedance. So this has to do with impedance matching and minimizing the noise. These are plotted against frequency, and as you can see, it works quite well. And again, when you see this, now we feel fairly confident. It really should be like this. It should not be like this, right? If we didn't really know the physics, we haven't seen more than one set of data, it's very easy to say, it should really be like that, right? Data is too simple. But now we actually feel very comfortable. Data really is probably quite good. Okay? All right, any questions about thermal noise? All right. Then another noise that's important is low frequency noise. And low frequency noise is the flicker noise, or 1/f noise that's important. And I think I've already gone through, we have already done this once, so we'll not go through again. But indeed, this is the model that's used in BSEM. It started with the kind of concept and parameters that one could determine from the telegraphic noise, and indeed was determined from telegraphic noise in terms of research, but in terms of getting the model parameter for actual production technology, engineers wouldn't go to telegraphic noise. They would just try to fit the model equation to the actual measured 1/f noise, of course, right? But to develop that 1/f noise equation, we actually did go all the way back to this telegraphic noise to understand the relationship between mobility fluctuation and number fluctuation. Turns out we confirmed they're the same. Those two are correlated as well, and able to include both in one model. So that's the model that you have seen before. That's used in BSEM. Start from study telegraphic noise using single trap. Model unifies number and mobility fluctuations, and has very unique bias and size dependence. And again, since we're supposed to be talking about compact model, let me just mention to you so that you know, if you take 6 different compact models, you're going to find probably 6 different 1/f noise or so. And you ask, gee, how is it possible that, shouldn't there be just one set of physics? Well, it's just really that complicated. First of all, physics is very complicated, and secondly, a lot of the engineers don't have the time to work out the physics. They just have to, check against the data to see this seems to work better. So let me just put this W squared in here, or Cox squared there. But I think physics is there, and if we have confidence in the physics, with time, people seem to converge to the correct physics. The data works out by themselves. Data sometimes it's well, all right. So that's the end of the review of the compact model, with some emphasis on the noise, because we haven't really talked about thermal noise, and some emphasis on the intrinsic inputting resistance, and a little bit about substrate network. Turns out those are what's important to make to understand and determines the behavior of the transistor. And just by adding those resistances, transistor model, as we understand it, does agree with data all the way very close to FT, tens of gigahertz. Okay. All right, questions about compact model? Okay, if not, I want to tell you about something that's related to this, but not quite exactly that. And this is the research, or one of the research topics that Kevin is doing. Kevin did a great job there. For a long time, we've been saying that a model like BSEM has so much physics in it, one can use it in a predictive manner. And there are many ways to say how you use it. One is to say how to translate the physical variation data from the fab. Let's say we know the sigma of Tox. Then we immediately import that into the compact model. We automatically know the variation of the transistor characteristics. That's great, and I think most people accept that and do that now. Another, which is what Kevin picked up to do, is much more aggressive and much more, I guess, questionable, and also we cannot have a too high expectation in terms of accuracy. That is this. That is, can we produce models for 0.1 micron devices so that the designers can use to do research right now? And can that user further, just on his own, with one keystroke, say, gee, I want to reduce VT by 0.1 volt, and then see how my circuit works, rather than waiting for TSMC to provide some data for this and still have some confidence the model is accurate, right? What if I have a technology whose oxide is thinner by 10 angstrom or something? And so this is called predictive compact modeling, all right? So what Kevin has done is he took a look at the BSEM parameters and divided it into 3 parts. One part he calls the process spec, things like delta L and L channel lengths, TOX, VT, and the source stringer resistance. These are basically things that someone have to at some point specify. Gee, I want this, our technology, our company is going to use this oxide thickness, right? We want to use this channel length, all right? Right? This is going to be delta L, that's going to be the VT. This is nothing that BSEM can predict this. Someone has to decide what they are, right? Okay, this is one set. He called process spec. Another he called the physical parameters. Now, if you know the TOX, if you know the VT, actually you can kind of figure out what channel doping should be, right? Right? Okay? And what the body coefficient should be, right? And knowing these things, knowing the depletion region thickness, we should know something about short channel parameters, right? This is a short channel parameter, short channel effect, that characteristic length effect, effectively is related. So there are sort of things like that, right? That we think we should be able to know how to scale with this. And finally, everything that's the rest of that is called secondary parameters. There are about 60 about those. Those are really just curve fitting parameters, trying to get the data close to 2% of accuracy compared with data. So we're going to assume these are unchanged because we think they have minor effect on the device characteristics. All right? You see what Kevin is saying? This is the process specs, right? And so if you're the designer, you have to tell us what you want. Actually, Kevin also tells you what he thinks at 0.1 micron technology these are. But in addition, he'll allow you as designer to select what you want. All right? Okay. And these then automatically Kevin's program will calculate, and then we'll put into whatever default value these are, and then give you this. Okay. And our hope is that this will be refined with feedback from IC companies, and Kevin will update his website and these numbers, and will continue to be updated. All right. So this is what he ended up doing, what he can do, and so verification with some data he obtained got from the literature. This is 0.18 micron Intel transistor IV curve, and the AEC 0.13 micron transistor IV curve. All right. And looking at the CV, you cannot fit as well. For example, in one case, significantly underestimated the capacitance. What we think is happening here is that this is probably quite strong retrograde, for example. You all know in the case of strong retrograde, for the same oxide, for same VT, you can get a smaller or larger XD max. Do you remember? With retrograde, you get a smaller or larger XD max? Larger. Smaller XD max, right? Smaller, I'm sorry. Smaller XD max, therefore larger capacitance. Isn't that right? Makes a lot of sense, right? So clearly this is also room for further improvement. Maybe, we can, Kevin can either assume at the generation onward all be retrograde, right? We can always do that, right? In this case right now, he assumes it's all uniform, right? Now that we have talked about it's going to be all retrograde, we can assume that, or we can even give the user a switch to decide which one, right? And we should make default, it's this retrograde, right? Then things will get better. But this is the kind of thing that one can do, right? So, and he believed that for each generation, he's going to get a lot of default value for that. But he allows the user to change L all the way from 200 angstrom to 1,000 angstrom, L effective. He thinks that actually works, all right? And L effective benchmark would be 800 angstroms. We say that because in this generation technology, at least for the processor manufacturers, they play tricks they actually produce gates that's smaller than this. And in addition, due to the overlap of the source stream with the gate, so the electrical channel length is actually quite small. So this effect is Kevin's reading what future technology would be like. These are future technology, what they be like, okay? So, but the user can change it within this. For example, what Chenming already put on the web, he thinks will be good enough for the designer to use to design transistors with 100 angstrom gate lengths. Now that's gutsy for him to say, don't you think? In other words, he thinks his model is going to be fairly decent as a predictor for future 100 angstrom channel length transistor, and good enough to use for research, circuit design research. All right? So that's called predictive modeling. Okay? So if you ever need a set of Beeson parameter, don't go anywhere else. Go to this website, and you will have your parameter. Okay? So his web access. This is the website. Okay? If you go to that, and this is what you see, and this site is going to prompt you to enter L effective, TOX, VT, and if you don't have this number, we have the default for generation, of course. Okay, and you know, probably in a minute or so, you're going to get this back, and that is first of all a set of IV curves, just so that you can see, you know, what this SPICE model is going to give you when you put it into the SPICE. Is this kind of IV, and give you a set of a model card. And model card is in the form that you can immediately load into the SPICE to do a circuit simulation. So we call this 1 minute model card. Okay, so you don't have to back TSMC for a year for a model card. You can get your model card in 1 minute. So you can customize delta L, TOX, VT, and RDS, and you can specify that. And let's see what else. Okay. What I did not mention to you is that actually Kevin also put in sort of a default capacitance model for the line to line or adjacent layer or in the same layer, and for local interconnect, for global interconnect, he also has some capacitance model, fairly simple capacitance model. So the hope is that the designer truly can have everything that's needed to do exploratory circuit design research. Okay. All right. So some comments about the compact modeling. Compact model, what user wants seems to be accuracy. They want speed. They want ease of parameter extraction. Those are what they want. And among these, I think accuracy is still what people really want. Speed, actually, when people really want speed, they don't get it by sacrificing the accuracy by going to simpler model equations. It's true, by using simpler model equations, simulation speed can improve. But perhaps you get 30% improvement, that's not enough. You know, what people really want is they want 100 times larger circuit to be simulated so they can simulate a full circuit, right? Not want 30% faster, although that's still useful. What they really want is to go to full circuit. And in order to do that, what people do is that they actually go to different simulation engine. They no longer do the kind of Newton-Raphson iteration kind of SPICE you do today. They actually do solve a particular time point actually using analytical solution. This is what you get when you use commercial tools like StarSims, like time mill, and that's what they can get 100 times, 1,000 times faster than SPICE we usually use in courses. But you know what? Those models, those time mill, StarSim, they still use Beeson. You first use Beeson to calculate the table for the IV, store those in the table so they can call out very rapidly. So in terms of accuracy, they still get from Beeson. And in terms of speed, they just use totally different simulation routine, not what you understand as how the Berkeley SPICE work. And that's how they get 1,000 times speed up, all right? And I think you will soon, pretty soon see some engine vendors going to claim they're going to have 10,000 times speed up. And so this did not come from the model. Model's first job is really accuracy. I believe that has to be the case, all right? Ease of parameter extraction turns out very important, but probably is too complicated a topic to discuss in a course. So we already talked about table lookup model, the pros and cons. Turns out table lookup is not most accurate. Most accurate, I still believe, will come from a a physically based analytical model, but people will actually generate table from that, strangely. Right? They won't get the table from measurement. They'll generate a table from that. That way they can have as fine a table as they wish, or whatever sort of table one wants. Predictive modeling capability is going to be useful, and we already talked about example what Kevin did. New device structure is always the issue. You know, people are seriously now talking about in the future we're going to vertical transistor, maybe double gate, maybe the source drain are not going to be symmetrical, and etc. How are we going to deal with that, right? And what about a role of a 2D, 3D simulation? For a long time, people have thought, you know, we can just solve the diffusion drift equation and combine that with some kind of spice engine so that we don't need to model any transistor analytically. We just use the 2D simulator to represent the transistor. And the hope was that, you know, with the simulation engine computer speed improving, that would be it. But the fact is that's not possible. Doing this today using the fastest Sun workstation, it's only practical to work with the simplest ring oscillator. In fact, when the student wants to simulate ring oscillator, guess how many stages he uses to simulate the ring oscillator. He will simulate 3 stages. That's all he can handle. All right, about 20, 30 transistors probably okay for that. So that is still far from that. Now, as far as this second to last bullet about new transistor structure, just happen to have this figure here. This is a 0.18 micron gate length, not electrical channel length. We don't know how short the gate channel length is, but the physical channel length is only 180 angstrom. All right, this is or was a world record. Was done by students here in Berkeley. We call that FinFET. In fact, it's a vertical transistor. Its current does not flow in a planar way along the surface, but along some vertical walls, and it's considered a very attractive potential new structure for the future. But what's interesting is that I just asked the student for fun, try to fit this IV curve of this transistor with BSEM, and this is what he got. So, you know, we don't think physics is going to change that much, and the kind of physics that we talk about here today, I think it's going to work for a long, long time. And indeed, there are certain things that doesn't work as well, and those will be obviously opportunities for further research. But I think the basic physics we know today, even if it's not totally, let's say, correct, for example, because we did not consider source side thermal velocity limit, but for circuit design purpose, at least, it seems that it can go quite a while. But let me give another example of the kind of models we haven't. Well, maybe I won't do this. Let's stop here and take 7-8 minutes break and come back for questions. All right. Now remember, on Thursday we're going to have a first midterm exam. So you may want to think a little bit about